Now we're going to start section 5.3. This is the section on open and closed sets. And the first lecture or so, where everything we're going to say is going to be just like something from section 1.6. Remember, 1.6 is open and closed sets in the real numbers. Now we're going to talk about open and closed sets in metric spaces. So let's write down the definition of a closed set. So we start out with a metric space. And we're going to let F be a subset of our metric space. We say that F is closed if for all sequences of point in F sequences in F that converge to some point in the metric space X, now we don't assume that X is also in the set X. What we're doing is we're saying any sequence in F that converges to a point, the point has to be in F. So here is an example. Let's let X be the real numbers and F be the set, let's say the interval from 2 to 7. This is the closed interval. If we've got a sequence of points in 2, 7, which converge, then you can write this a couple of different ways. X is the limit of the xn's, but for any convergent sequence, that's the same as the limit supremum of the xn's. That's the limit as n goes to infinity supremum over k at least n xk. We remember this is how lim sup is defined, which is certainly not going to be bigger than if you take the supremum of all of them, but they're all in 2, 7, so 7 is an upper bound. And similarly, if you converge in the real numbers, your limit is your lim inf, which I'm not going to write out the entire argument. It's pretty much the same as at least 2. So X is in 2, 7. So we've seen that any sequence of points in 2, 7 that converges, it converges to a number in 2, 7. So 2, 7 is closed. Another example. Let's stay in the real numbers for a little while, because that's where we're comfortable where all the straightforward examples are, let's let f be an open interval. And I'm going to let 0 be one of the endpoints just because that makes this a little easier to state. And let's let xn be the number 1 over n. Then our sequence of xn's, that's a subset of f, and xn converges to 0, but 0 is not in f, so f is not closed. Now let's have an example not in the real numbers. Let's let x be the rational numbers instead. And let's let f be this interval. We'll take this. It's a half open interval in the real numbers from 0 up to the square root of 2. Sorry. And then that's a set of real numbers. I don't want that, so let's intersect that with the rationals. And we can write this as the set of all rational numbers such that q is positive and also q squared is less than 2. Then f is closed in Q. It is, if you think of f as a subset of the real numbers, it's not closed. It's got the square root of 2 as a limit point that it doesn't contain. But if you think of it as a set of rational numbers, it is closed. So certainly you're going to have some sequences of points that are converging in the reals to the square root of 2, but they aren't converging to the square root of 2 in the rationals because the square root of 2 isn't in the rationals. So this counts as a closed set. Now we are going to define open and closed balls. You remember in the reals, we spent a lot of time talking about intervals that look like x minus r up to x plus r. This is the analog in a metric space. So let's let xd be a metric space. And then we pick a point in our space and a positive real number. And then we're going to write the ball centered at x of radius r. That's the set of all points y in the same metric space such that the distance from x to y is strictly less than r. And what we call the closed ball centered at x of radius r, that's the same thing, except with a less than or equals to. So let's have a couple of examples of what I am getting at. So first off, if x is the real numbers and we take the usual absolute value metric, then the ball centered at x of radius r, that is the open interval from x minus r up to x plus r, and the closed ball is the closed interval. So here is another example. If x is r2 and our distance is the usual Pythagorean metric, then the open ball centered at x of radius r looks like this. We're going to start with our point x here. Then you draw the circle around it of radius r. And then the open ball is you just fill it in. You get everything inside, but not on the boundary. And the closed ball, you would again start at x and draw the circle of radius r that you know from geometry around it, but this time you would get to keep the boundary in addition to all the stuff in the inside. And in fact, the exact shapes of balls can depend on the geometry, on your metric. So if we're going to take the same set, R2, because it's easy to draw, and then we'll say the distance from x to y is, we're going to take just the coordinate distances and just add them without doing any squaring. Then in this case, what balls end up looking like is they end up with these sort of diamond shapes. And one last example of balls, if xd is discrete, meaning we're using the discrete metric. So remember, this is this sort of space where you've got all your points are a unit distance apart. And a ball, then a ball centered at this point of radius r. It's everything that's a distance less than r from this point. And you'll notice that if r is small, that's just this point. And if r is big, it's everything in the entire set. So the open ball centered at x of radius r, it's going to be just the set containing x, or it's going to be the whole space. It's going to be just the set containing x if r is less than or equal to 1, and it's going to be the whole space if your radius is bigger than 1. And then the closed ball, it similarly is either the single point x or it's everything, except there's a slight difference. Here it's the single point if r is less than 1, and it's the whole space if r is greater than or equal to 1. So notice one of the weird things about the discrete metric is that the closed ball and the open ball can actually be equal to each other. Now, there are two ways to define open sets. I think I'm going to do this a little bit differently from your book. I'm going to start by proving that the two ways of defining open sets are equivalent, and then we'll just say that any set that satisfies either condition is open. So let's let XD be a metric space. and we're going to grab a subset of it. And it's sort of traditional to call closed sets F and open sets G. I don't know why. Then the following two things, then the set X minus G, so the complement of G is closed in X if and only if for every point little g in our set G, there is a positive number R such that the ball centered at X of radius R is contained in G. And then if either condition is true, and since they're equivalent, if both of them is true, we say G is open. So let's prove this. This is pretty similar to a proposition back in section 1.6, which I'm sure all of you remember completely in every detail. I am not sure of anything of the sort, so we'll give another proof. Maybe I'll use a slightly different proof from what I gave in the video last semester. So let's suppose that this complement is closed. And we're going to pick some point X in G. And what we're trying to do is we're trying to prove that the stated condition, why don't I give it a name? We can call it condition star. We want to show that condition star is true. So we want to show there is a positive real number such that the ball centered at X of radius R is contained in G. Now I can tell you what R is. Let's go ahead and let R be the infimum of the set of all distances from X to Y, such that Y is in X minus G. Or, now there is one technicality here that I want to cover. Or if X minus G is the empty set. The empty set is a closed set. All of the sequences in the empty set converge to things in the empty set. That's because there's no sequences in the empty set, so you can say anything you want to about them. In this case, we want the infimum is the greatest lower bound. Technically, the infimum of the empty set is positive infinity. We don't want that. We'll pick, in this case, we can pick a radius R equals 1. So then, and first thing we need to show show two things. We need to show that R is positive, even if X minus G is not the empty set, and we need to show that the ball centered at X of radius R is contained in G. And the second of those is actually easier to prove, so let's get it out of the way. If Y is in the ball centered at X of radius R, then the distance from X to Y is less than R, which is, I suppose, technically less than or equal to the infimum. I'm going to write Z not in G instead of Z in X minus G. So Y is not one of the points in X minus G because those are all a distance more than at least r from x. So y is in G. And so in either case, the ball centered at x of radius r, that is contained in G. So that's one of the things we wanted to prove. Now we just need to show that r is positive. All right. And if G is all of x, if f minus G is the empty set, we're done. We picked r equals 1. So now we're going to assume x minus G is not empty. That means, in particular, r has to be finite because there's at least one distance, and distances are always finite. So, for each positive whole number n, r plus 1 over n, it's bigger than the infimum, so it's not a least upper bound. So if n is a natural number, then r plus 1 over n is not a lower bound. So we can let yn be a point in x minus G with the distance from x to yn less than r plus 1 over n, because r plus 1 over n is not a lower bound. And there yn exists. All right, now let's think about the yns. The sequence of yns, we've got a list of numbers, we can make them a sequence. This is in x minus G. X minus G is closed. And x is not in x minus G. So yn cannot converge to x. It's a sequence in a closed set, so if it converges to anything, it converges to something in the closed set, so it's not allowed to converge to something not in the closed set. And let's write out carefully the epsilon n definition of not converges. We went over this a few times last semester. So there exists a positive number epsilon such that for all natural numbers n, there is a little n that's at least r big N such that the distance from y sub n to x has to be at least epsilon. But the distance from y sub n to x, that we assumed was less than r plus 1 over little n. And because little n is bigger than big N, this is at least r plus 1 over big N. So we've got that. So epsilon is less than r plus 1 over n for all n. And you can check that means that epsilon is, that means that r is at least epsilon, which is positive. So r is positive. And so we've found a positive number such that the ball centered at x of radius r is in G. And since it's a and that is our condition star, so we can write that star holds. And now let's prove the converse. So we suppose that our condition star holds. And we're actually going to prove basically the contrapositive to being closed. Let's let X be a point in our metric space. X is not in the thing we're trying to show as closed. That means that X is in G. And we're going to grab a sequence of points in X that converges to our target point that's not in our thing we're claiming it that is closed. And then what do we want to do? We want to show that this sequence is not a subset of X minus G, because if it was a subset, because by the contrapositive, that means that if you've got a subset of X minus G, then it can't be converging to this point in G, and therefore therefore if it converges at all, it has to converge to something in X minus G. So rather than showing that all sequences that converge to something in X minus G, we're showing that all sequences that converge to something not in X minus G, they don't start out in X minus G. So now, by our condition star, there is a positive number R such that the ball centered at X of radius R is contained in G. And since R is positive and Xn is converging to X, there is a natural number N such that, well, usually it's a statement for all little n bigger than big N, but we only really need one of them, such that the distance from X to Xn is less than R. So Xn is in the ball centered at X of radius R, which is contained in G. So Xn is not in X minus G. So our sequence is not a subset of X minus G. Thus, if you've got a sequence that is a subset of X minus G, then Xn does not converge to X for all X in G. So if Xn is a subset of the thing we're claiming is closed, and Xn converges to Y, then Y can't be X because Xn doesn't converge to X for all X in G. So Y is not in G. So Y is in X minus G. So X minus G is closed. And that completes the proof. Here is another proposition that is pretty much a verbatim, that is just like a proposition in section 1.6. This is proposition 5.3.2. It's just in a metric space instead of the real numbers. And then, first off, if F1, F2, up through Fn, if these are all are finitely many, I want to emphasize we've only got finitely many of them. And they're all closed subsets of X, then their union is closed. And conversely, if I is any index set, this is either finite or infinite. And it can even be an uncountably infinite set. And for each k in our index set, we let f sub k, or we have f sub k is a closed subset of X. Then the intersection of all the f sub k's is also closed. So you can take finite intersections, infinite intersections, countable intersections. If you came up with an uncountable collection of closed sets, their intersection would still be closed. And if you want unions, you need to take a finite collection. And the case of open sets is exactly the opposite. I guess I have done this not quite in the order and way he did it. So part B is if you've got in open subsets of X, then the intersection of finitely many open subsets is open. And I'll say one thing about the proof of this. You grab a point in the intersection, you let your radius for the intersection be the smallest of the radiuses of G1 up through Gn. And that works. But you can only do that. You can only take the smallest radius and expect to get a positive thing if you've only got finitely many of them. If you've got infinitely many of them, they can all be positive, but the infimum can be 0. And then, however, you can take infinite, countable, uncountable, whatever unions. This is finite or infinite. Then the union is also open. And I think in this case, I will not drag us through the proof again, and I will just ask you to go back and read the proof of proposition 1.6.3 in section 1.6. Next, I want to say one more thing about these things I've been calling balls and closed balls, or open balls and closed balls. Here is a proposition. Your book thinks it's an example, but XD be a metric space. And then we're going to pick a point in our metric space and a positive radius. Then the ball centered at X of radius R is open. And this B bar centered at X of radius R is closed. And the proof is pretty quick. Let's let Y in the ball I'm claiming is open. Then rho is R minus the distance from X to Y. Well, the regular ball, the open ball, means the distance from X to Y is less than R, so this rho is positive. And if Z is in the ball centered at Y of radius rho, then the distance from Z to X, just use the triangle inequality. And this is less than rho. And then the distance from X to Y is, in fact, equal to rho plus R minus rho, which is R. So we have that Z is in the ball centered at X of radius R, since the distance from X to Z is less than R. So that means that the ball centered at Y of radius rho is contained in the ball centered at X of radius R. So for every point Y in the balls in BXR, there's a little ball centered at Y that's in BXR. So BXR is open. Now let's prove that the other one is closed. And let's suppose that xn converges to, we've used x already, so let's suppose it converges to y. And then for any natural number n, the distance from y to x, that's less than or equal to the distance from y to xn plus the distance from xn to x, that's less than or equal to, let's leave this first one alone, but the distance from xn to x is less than or equal to r. And now xn is converging to y, so for all epsilon greater than 0, we have that there is a n with distance from y to xn being less than epsilon. So for all epsilon greater than 0, the distance from y to x is less than r plus epsilon. The only way that can be true for all positive epsilons is distance from y to x has to be less than or equal to r, and y, that's exactly what it means for y to be in this closed ball. And so we've seen that for any convergent subsequence of what I'm claiming is the closed ball, the limit point is also in the closed ball. So that means that our closed ball is in fact closed. Last thing I want to do is to tell you what your homework is going to be. So here's how it's going to work. We let XD be a metric space. And we're going to let Y be a subset of X. Then YD is also a metric space. Basically, you inherit all the axioms for the metric, and if the distance is defined for any 2 points in X, it's certainly defined for any 2 points in Y. So if G is a subset of Y, and G is open in the metric space YD, we say that G is relatively open. And we define relatively closed in the same way. And I'm going to give you a couple of examples of relatively open and relatively closed sets, and then you'll prove something about them on the homework. So here is an example. Let's let X be the real numbers and Y be the rational numbers. And then this set then the set that is, let's say, 0 square root of 2 intersect the rational numbers. That's the set of all rational numbers that are non-negative and whose square is less than 2. That is relatively closed. We talked about this a little bit earlier in the lecture, but the point is all the subsequences in F that converge in Q, well, in Q they are not converging to the square root of 2 because the square root of 2 isn't Q, so in Q, so this counts as relatively closed. And you can also write G minus root 2 intersect Q is relatively open. And let's have a slightly more pictorial example. So here is going to be our space X. Everything in here. And then we'll let Y be the bottom half, and we'll include some but not all of the boundary. And then let's say this set G, it's including some of its boundary, but nonetheless, that's relatively open. And this set, let's put a set F over here. This is missing some of its boundary. You can think of closed sets as including the boundary, open sets as not including the boundary, and we'll make that notion precise in the next video. But this set, it's missing some of the boundary, but the bit of its boundary it's missing, its part is also missing from Y, so it still counts as closed. G includes the boundary, but sort of a funny, but that's okay. If you grab a little point here in G and you draw a little ball around on that, well, you may be missing this part of the ball, but since this part of the ball is missing from Y, that's okay. G still counts as relatively open.